are beginning part 2 of the unification of physics. In the previous video, remember that we discussed classical physics. Newtonian mechanics led to a theory of gravity. Newton provided us with this simple formula. Any two pieces of matter attract one another with a force that's inversely proportional to the square of the distance between them. It was an action at a distance formulation. Newtonian mechanics was entirely predicated on 3 notions, space, time, and matter. Maxwell unified optics, which is the theory of light, electricity, and magnetism. He combined them into electromagnetism. It's a field theory, which is at odds with Newton's action at a distance theory. There was a problem between Maxwell's theory and Newtonian mechanics, and so something had to be done about reconciling them or getting rid of the contradictions between them, and that was done by Einstein in his special theory of relativity. He removed the contradictions between Newtonian mechanics and Maxwell's theory by unifying space with time. We could no longer think of time and space as separate notions. We had to think of space and time as one entity. Einstein's fix only applied to inertial reference frames where 2 observers were moving at a constant velocity relative to one another. So if you're still wondering about any of these things on the left side of the ledger and don't know what I'm talking about, you should go to the first video and review what was developed there, and then you'll understand what's on this side. We discussed nothing about quantum physics, and we're going to remedy that in this video. In particular, we're going to discuss the events that led to the requirement for a new theory. Our goal is to see how the general theory of relativity emerged from all the discoveries that went before it, and how it became our theory of gravity and the physics on the large scale. And we'd also like to know how the Standard Model emerged from all the physics and discoveries that went before it. In this video, we'll go some of the way there. We won't get all the way there. If you remember, general relativity and the Standard Model are logically incompatible. The underlying mathematics that supports them is not the same. And what we would like to do is find a way of combining them into one theory, one consistent theory, euphemistically called quantum gravity. It doesn't exist yet, but that's the goal. And that's what we mean when we say the unification of physics. If you'd like to know more or get more detail on this subject, you can go to my website at www.roadtoatoe.net, and there you'll find 4 books that you can access and read that goes into much more detail than we will in these videos. So let's get started with part 2. The first indication that classical physics may have some problems came in the form of the researches of Max Planck. He studied blackbody radiation. So what's that? The Earth acts somewhat like a black body, not quite, but somewhat. The Earth's air close to its surface has something called ambient temperature. Ambient. It's kind of the average temperature of the Earth. And that ambient temperature, average temperature over the whole of Earth, stays pretty steady. It's probably about 55 degrees Fahrenheit. Climate scientists measure this. And so what that indicates is that the Earth absorbs about as much energy as it emits. And again, this is over the whole surface of the Earth. There are hot spots on the Earth and the cold spots, but the average temperature stays at about 55 degrees. Of course, climate scientists are concerned because the ambient temperature of the Earth is rising, and that creates significant weather events. Max Planck, he was studying blackbody radiation primarily to make a perfect light bulb. It was his researches in this that began the revolution in quantum physics. As you'll remember, Maxwell told us that light was a wave. And light can come in many different wavelengths, or if you want to say it another way, many different frequencies. And a frequency is just how fast the wave oscillates. If it oscillates slow, it's got a low frequency. And if it oscillates really fast, it has a high frequency. On this graph, a high frequency would be out there somewhere, and a low frequency would be back there somewhere. Now, the classical law that covered blackbody radiation was embodied in the Rayleigh-Jeans law, and it was derivable from Maxwell's equations. It made good predictions at low frequencies, but not at high frequencies. Light with a with a higher frequency has more energy. The Rayleigh-Jeans law predicted as the energy rose, as the frequency of that light increased, the body would just continue to get hotter and hotter. What Planck and others noticed was that, well, that really didn't happen. If the Earth just kept getting hotter and hotter, we just couldn't live here. So what Planck understood was that there was something that caused the body to reach equilibrium, where it absorbed as much energy as it gave off, kind of like the Earth. And his task was to try to find an equation that better described what really happened instead of the ultraviolet catastrophe inherent in the Rayleigh-Jeans law. What Planck did is he came up with this formula. I don't know if you can see this, as opposed to this is the Rayleigh-Jeans formula here. And you can see as the temperature goes up, it just goes off to infinity. But this cools off as the frequency increases. The black body gives off about as much energy as it absorbs. This formula involves statistical analysis, and there was this damping, this piece here that you don't see over here, that allowed the curve to bend downward like that, instead of just going off straight line up to infinity. In order to make his law work, he had to assume that the energy in these waves came in what we call a Planck unit of energy. The energy is equal to this constant. Would later become known as Planck's constant, and this is the frequency of the radiation. What was interesting about this is that the energy absorbed by a black body comes in integer units. When I say integer, I say 1, 2, 3. Comes in integer units of Planck energy. What we didn't see is energy like this, 1/2 h nu, or never saw 1/4 h nu, or 3/4 h nu. That never happened. It always came in discrete integer multiples of energy. Planck did not realize the revolutionary aspect of his theory. He believed in the wave nature of light. He was troubled by this aspect of his theory. No one realized the significance of what he had discovered until later. This would become the basis of quantum mechanics, particularly this constant. This constant is extremely small, something like 10 to the minus 34 joule seconds or something. I don't exactly remember, but this was the beginning. The next big event was produced by Einstein in 1905. He published 5 papers. This is just one of them, what eventually became known as the photoelectric effect. What is that? Well, if you look at this setup, this is sort of like a vacuum tube with a piece of material, gold foil or something, or some sort of foil. Then you have a device that shines light on the foil. If you begin increasing the frequency of the light up to a certain point, say right there, and when you get to that point, we're just going to call that frequency nu 0, a current begins to show up. Electrons were being knocked out of the material, causing the current. Now that didn't square with the wave theory of light, because if you had light coming in and it was hitting an electron, say, the electron would just sort of bob up and down, maybe vibrate, but like a boat sitting on the water, it wouldn't push the electron this way if the light was moving that way. It would just you just sort of see it floating along. There had to be something else, some other explanation. And the explanation that Einstein gave was that light was particle-like, that it was these little pieces of particles that look like this, that hit an electron, here's the electron, and knocked it out of the foil or the material. His analysis was that light were little pieces of energy. And interestingly enough, those little pieces of energy come in energy packets that Planck had discovered in his black body researches. So it looks something like this. You had energy on this scale up here, and then the frequency here along this scale. And what would happen is that as you increase the frequency of the light, it would get to a certain point, say right here, that depended on the material, and then you would have a line whose slope was h as you increase the frequency. So the electrons would be bounced out of the material with greater energy as the frequency increased. And so it comported with Planck's units of energy. This is the paper that Einstein won the Nobel Prize with. It wasn't his paper on relativity or special relativity, it was this paper. In 1905, everyone still believed that light was a wave, and so Einstein's paper was pretty much ignored until about 1923. Arthur Compton showed that Einstein's analysis could actually experimentally be shown. How he did that was he shined light scattering the electron, and the energy in the light after the scattering was conserved. And the only way that that could happen is if light was particle-like. This was a particle phenomenon here. Particle. We didn't have any light theory that looked like this. The electron was at rest, and this had so much energy in the wave, and after the light collision with the electron, the energy in the electron plus the energy in the wave was the same as before the collision. This was not a light phenomenon. This was a particle phenomenon. About 2 decades after Einstein published his paper on the photoelectric effect, Louis de Broglie proposed that not only did radiation exhibit particle properties, but particles exhibited wave properties. De Broglie's equation the wavelength of a particle was proportional to the inverse of its momentum. This was just when you have a wave, this is lambda. And the momentum of a particle is just P equal to m times v, which is the velocity, mass times velocity. And so the wavelength of a particle was related to the momentum of a particle by this equation here. No one had ever seen an equation like this. There were wave equations that described the behavior of waves, and there were particle equations that described the behavior of a particle, but no one had ever seen an equation where waves were related to particles. And this happened to be de Broglie's doctoral thesis. The doctoral examiners didn't know what to make of it, and so they passed his thesis on to Einstein for evaluation. And Einstein endorsed it, and so de Broglie got his PhD. Now, if we look at this equation a little closer, we can write it as P is equal to Planck's constant over the wavelength. And then if we were to multiply both sides of the equation by a velocity, P v, velocity, v, is equal to h over hv over lambda, the wavelength. And if v is equal to c, this then would be equal to hc over lambda. If we call this, we're cheating here a little bit, the energy, E, that would be equal to hc over lambda. But c over lambda was just equal to the frequency, and so this became h nu, where nu is equal to c over lambda. And this was Planck's discrete energy. So that's how it relates to de Broglie's equation. Now, I've cheated a little bit. This equation here is actually a relativistic equation, and P is normally associated with a particle that has a mass. According to the special theory of relativity, a particle with mass can't reach the speed of light, and I've substituted the speed of light in here. If we ignore that, then you can see the relationship between Planck's energy levels and de Broglie's equation. And so now we had the situation where not only did light have particle properties, but particles have wave properties. Now, a few years later, physicists invented what they call an electron gun, and it's basically the same thing as the vacuum tubes that were in the first black and white television sets. The experiment that they conducted was to shoot these electrons, which were assumed to be particles, through two small openings and onto a detector screen. If we shot particles through 2 small openings, whether the machine gun bullets or paintballs or whatever these particles were, we'd expect to see this pattern show up, where the particles that made it through the slits created this kind of pattern on the screen. Now, if we did the same experiment with light, it was a wave, wave, so it would spread out. And when it went through two little slits right here, this part of the wave would go through this slit at the same time as the other part of the wave would go through this slit, and it would diffract, spread out, and create these interference bands on a detector screen here. That's what you would expect to see if whatever you shot through the two slits was a wave. This experiment, they shot electrons through the two openings, and what they expected to find was this pattern here, because electrons were particles. What they found was that pattern, and that was surprising. They didn't expect that electrons would behave like a wave. And the question was, if two pieces of the wave go through the openings at the same time, how did an electron, a particle, go through these two openings at the same time? That was the dilemma that existed in trying to explain what was happening here. So what the physicists did, they shined light of a certain energy. You know, here's a flashlight here, and the light's coming out here. A light of high enough energy would be able to see which opening the electron went through, and they could actually see if it was going through both openings simultaneously. So when they did this, they saw electrons behaving like particles. Some electrons went through this slot, and some electrons went through that slot, but no electrons went through both slots at the same time. There was a 50% probability the electron would go through this opening, and a 50% probability that the electron would go through the other opening. But something else strange happened. When they did this, when they shined the light and saw which opening the electron went through, the interference pattern on the detector screen disappeared. It became problematical to describe the electron before it interacted with this measuring device. What was the electron before that interaction? Was it a particle or was it a wave? And you simply didn't know which it was until it interacted with this measuring device. Those measuring devices designed to see the electron as a wave would see the electron as a wave. Those designed to see the electron as a particle would see the electron as a particle. It was impossible to say whether the electron was a particle or a wave, and this became known as wave-particle duality. Now, de Broglie also came up with the concept of a wave packet, and it looks like this. And this wave packet travels through space at a velocity v, and it can wobble and spread out, or it can just stay intact. Now, if I wanted to measure the velocity of this wave packet, I had to have a measuring apparatus that could see the whole thing. And since velocity was associated with momentum, that's how I had to measure the momentum of this wave packet. But what if I wanted to determine the particle properties of this wave packet, the electron, for example? So the electron would vibrate along like this. And in order to know where it was at any moment in time, I'd have to shrink this wave packet down to a very small area. And that would give a better estimate of where the particle was at any moment in time. But it was hard to see that if I squeeze this down into a very small area, how I could measure the momentum and this location at the same time. So, for example, I could say that the electron was somewhere in here. So I would just sign this distance here, delta x. Delta x represented the error that I would make in trying to determine where the electron was in space. On the other hand, if I collapse the wave packet down into a very small area, that would give me a better measurement of position, but create a huge error in momentum. It would be harder and harder to measure momentum. So the error in momentum then would just be delta p. And if we plug these things into de Broglie's equation, this one, we're going to put delta x in for lambda, that's the wavelength. And so we would put del x in for lambda, and then del p in for p, the momentum. That's going to be, I'm going to write greater or equal to h. If you look at this, if we want an exact measurement of position, which would be delta x, this would be h over delta p. So if we wanted exact position, this to be really, really small, this would have to become really, really big. And the way it was interpreted, it would have to become indefinite. If I wanted to get an exact measure of position, I couldn't get a measure of momentum. And vice versa, if I wanted exact momentum measurement, I would get an indefinite position measurement. That suggested that trying to measure position and momentum simultaneously was not possible. The error in it would be at least as great as this. The error in measuring both position and momentum at the same time had to be at least as great as h, Planck's constant. That became known as the Heisenberg uncertainty principle. This became a fundamental law of quantum mechanics when quantum mechanics was eventually developed. De Broglie called the thing that he had discovered a matter wave. Those were particles with mass that had wave properties. Physicists eventually decided that what these matter waves really were atoms. Back in about 1827, while examining grains of plant pollen suspended in water under a microscope, Robert Brown, he was a Scottish botanist, observed that the minute particles executed a continuous jittery motion. He thought that he had seen certain motions in these particles that had to do with life. But then he observed the same motion in particles of inorganic matter, and that enabled him to rule out the hypothesis that the effect was life-related. Although Brown didn't provide a theory to explain the motion, it eventually became known as Brownian motion. In 1905, guess who? Einstein took up Brownian motion. At that time, the positivist philosophical crusade had emerged, and positivists argued that the multitude of metaphysical arguments sprinkled throughout physics was the primary source of theoretical errors. The only ideas that should find a place in physics were those that could be verified through sense experience, validated in some way. And the positivists at the time supported the view that atoms did not exist because they were unobservable. Einstein was able to determine the size of atoms and how many atoms were in a mole and their molecular weight in accordance with other laws that are around at the time. Einstein's paper is widely credited for providing proof that atoms were measurable objects, and that fit the requirements of the positivist thinking at the time, so they were much more open to accepting the idea of the atom. Now, the first attempt at describing the atom came from J.J. Thomson. He was quite famous because he was the one who discovered the electron. He called it a corpuscle, but he won the 1906 Nobel Prize for that discovery, and the Queen knighted him, so he was known as Sir J.J. Thomson. And his model was called the plum pudding model. And it looks something like this. He imagined that his corpuscles, or electrons, were submerged into a pudding of positive charges. And it was the arrangements of the electrons that defined the elements. If you put molecules of the same element in a gas, they show what they call spectral lines that line up, looks, something like this. Thomson hypothesized that the different arrangements of the electron in the pudding created different spectral lines that identified each element. That gave some credence to his model. Now, later, in probably 1909, Rutherford, Geiger, and Marsden decided to test the Thomson model. Now, what they did was to take alpha particles. Those are helium nuclei. They have a +2 electric charge, and shoot them through a material. And what they expected to find was that these alpha particles would only be deflected. They put them onto a detector screen here, and they would only be deflected a little bit or not at all. But when they conducted the experiment, most of them went through straight through without being deflected at all, or not very much. But certain alpha particles that were very close together were deflected at angles that didn't square with the plum pudding model. And some bounced back at angles that were markedly different than what you would expect. And so Rutherford published a paper that disagreed with Thomson's model and proposed a miniature solar system model, actually up here. It looks something like this. He hypothesized that there was a small central core surrounded by electric charges that circled around And he was able to calculate the speed and energy that the electrons would need to stay in orbit around the positive core. And he did this only with the hydrogen atom, one proton and one electron. He was able to predict the correct energy levels of the hydrogen atom. Now, the Rutherford model had some defects. Maxwell's theory had predicted that accelerating electrons would give off radiation. If that was the case, they would lose energy and eventually spiral into the nucleus, making the atoms unstable. It was pretty obvious that atoms weren't unstable. In addition, his model couldn't predict the spectral lines of the hydrogen atom. If the electron was spiraling in to various continuous energy levels, eventually crashing into the nucleus, the atom wasn't stable enough with this model to be able to see these spectral lines. Rutherford was on the verge of giving up the idea, the miniature solar system model of the atom. But then a short time later, Niels Bohr became his understudy, worked with him. Bohr saved the miniature solar system model by hypothesizing that the electron going around the nucleus of an atom, here's the nucleus, would not spiral into the nucleus if the electron circled with an integer number of de Broglie wavelengths. Remember, de Broglie's equation was something like this, Planck's constant over the wavelength. If we multiply both sides of that equation by v, we get PV is equal to HV over the wavelength. That's just the energy, so we can say that E is equal to H, but this is just the frequencies. That's how it relates to Planck's energy units. The wavelength has to come in integer multiples of de Broglie wavelengths, so if we figure out what that looks like, we would have integer number of wavelengths is equal to the circumference of the circle is just 2 pi r. The wavelength is equal to 2 pi r over n. So if we plug that into this formula, we would get P is equal to H over 2 pi r over n, and that would be equal to P n H over 2 pi r. Now, we usually signify h over 2 pi as h bar. The momentum of the particle has to be equal to n h bar divided by r. Now, if we multiply both sides of the equation by r, we get p r is equal to n h bar times r over r, but these cancel and we just get n h bar. And usually this is classical definition of angular momentum. We usually call it L. And that means the angular momentum of the electron comes in integer units of h bar. The electron would go around in this pattern rather than a circular pattern. It can only assume these values, integer multiples of h bar nu. And so the electron wouldn't spiral into the nucleus because it could only assume certain values. It couldn't assume anything in between. And so it was prevented from spiraling into the nucleus. And when it did change energy levels, it would jump instantaneously from one energy level to a permitted energy level while giving off radiation was an integer multiple of h nu. It was kind of strange that it would jump from here to here or from here to here, giving off an integer number of Planck energy units in radiation when it lost energy. That saved the Rutherford model from the scrap heap. Not only was Bohr able to predict the correct energy levels, but he was able to show for the hydrogen atom the correct spectral lines. Bohr's model was really kind of the first quantum mechanical model, where these discrete energy levels were the only ones that the electrons could assume. So let's see where we are in our adventure to see what the unification of physics is all about. All the events and things that happened that we talked about in this video were all indications that classical physics bore serious flaws. In the previous video, we had reviewed some of classical physics from Newtonian mechanics down to the special theory of relativity, and we have looked in this video at the events that occurred that begged for a different kind of theory to explain the physics on small scales. In the next video, we'll talk about the development of non-relativistic quantum mechanics. We would like to get to this place. We have talked quite a bit about the development of classical physics, we have not yet talked about how Einstein developed general relativity into a theory of gravity. In this video, we've taken a few steps toward the standard model. We haven't talked about non-relativistic quantum mechanics, and we'll need to talk about that as well as relativistic quantum mechanics before we can start talking about the standard model. In the next video, we'll talk about non-relativistic quantum mechanics. So be sure to tune in.